Hello and welcome! In my last video I repaired this Biostar MB8500 TVX mainboard, which will serve us today as a nice platform for an experiment which I planned to do since quite a long time. Aside from physical damage, this board was missing some socketed ICs, if you remember, one of which was the real-time clock module. If you watch my channel regularly, you will know my self-made RTC module, which I open-sourced and presented a long time ago. It is basically a drop-in replacement for the well-known black boxes from Dallas, Benchmarq and other compatible RTC modules, which will be the main topic today. First of all, let's talk a little bit about the history of the real-time clock circuit on an IBM PC and compatibles to understand better how we ended up with those black boxes at all. IBM introduced onboard real-time clock circuits with the first 286-based PC-AT in 1984, and it belongs to standard on all compatible systems ever since. The first implementation has been used more or less unchanged up to early 486 PCs and was made of 3 circuits: the real-time clock chip, the clock generator circuit and the power supply. The RTC chip was not only responsible for keeping up the time and calendar running, but had also some integrated general-purpose memory, which was used to save the BIOS settings, for example. That is why most of the PC mainboards don't even initialize without an RTC chip. On the early IBM PC compatibles, usually a Motorola MC146818 or Hitachi HD146818 were used. Basically, same chips made by different manufacturers. Let's take a brief look at the pinout of such an IC without going too deep into details. On pins 4 through 11 it has 8-bit shared address and data bus. This is how clock, calendar and internal memory can be accessed. Of course, we can control read-write operation using the pin 15, set the bus to data or address mode using pins 14 and 17. Other interesting pins are Reset, Interrupt and VCC. This IC can also generate a square wave and has some control pins for that. We will come back later to this pinout, but first we are interested in pins 2 and 3. Like any other quartz-driven watch on your wrist, also a clock in a PC needs some kind of frequency generator which would trigger the circuit periodically. This is what the pins 2 and 3 are for, an external oscillator. And here we come to the second part of the RTC implementation, the oscillator circuit, which is made of a 32 kHz crystal oscillator, capacitors, resistors and an inverter which is needed to convert the weak sine wave generated by the crystal oscillator into a steady square wave, which is then fed into the RTC chip on pins 2 and 3. Of course, we want that the clock is running even if the main power is off. That's why we need the third part of the circuit, battery power supply, which is made up of a couple of resistors, diodes, caps and 2 transistors. This power supply not only keeps the oscillation running when the main power is off, but also powers the RTC chip on pin 24, which is specified for voltages between 0.3 volts and 7 volts. So theoretically, this whole setup should run even if the battery charge is very low. That's why those circuits could run with the same battery for 10 years or more. So this was a brief overview of the first RTC circuit implementation as you could find it on the most 286, 386 and even some early 486 PCs. However, as we all know, the industry is always searching for ways to reduce the costs, and so some work has been done to reduce the amount of external components required to implement this. First of all, the power circuit, which contains quite a lot of standalone parts to control the switch between the battery and the main power supply to avoid the battery drain when PC is turned on. So a new RTC IC has been introduced which closely met the functionality and the pinout of the previously used Motorola MC146818, but brought some additional functionality. Dallas DS1287 was one of the names of the new chip. It was equipped with more general use memory, which was required, for example, for the BIOS settings and initialization, but also it reused some previously unused pins to connect the battery. Previous pins to control the square wave generation were deprecated, and instead pin 20 was now used for the battery plus and pin 16 for the battery minus poles. The VCC pin 24, which previously was used to power the IC from an external power circuit, was replaced by a normal 5-volt power supply. Now the RTC chip got two inputs for the power supply, one from the main and one from the battery power supply, and the circuit to switch between those was moved from the mainboard into the IC. The same procedure has been made for the oscillation part, and now only an external crystal oscillator was needed on pins 2 and 3. However, the requirement was to keep the extremely sensitive crystal oscillator as close to the chip as possible. But for stability reasons, most of the manufacturers added some additional capacitors and resistors though. And this one IC solution was then used on 486 and some Pentium PCs, where you could usually find a CR2032 lithium cell coin battery and a crystal oscillator connected to a Dallas DS1287 or compatible chip. This was of course not the end of the story. At that time, some old PCs with rechargeable batteries started to fail due to leaky batteries and expensive damage on the mainboard. Of course, that had nothing in common with the new solution, which used lithium CR2032 cell coin batteries, which almost never leaked. However, the whole story brought the industry to a glorious idea how to make even more money. Changing a CR2032 battery is easy and everybody can do it. You don't need to buy new parts or call an expert. So the manufacturers of the RTC chips decided to make an all-in-one solution. The RTC chip, crystal oscillator and a small coin battery soldered directly to the pins of the IC. Everything packed then into a plastic housing and filled with black resin, so that nobody is ever able to replace the battery and is forced to buy such a new RTC module every time a low battery message appears on the screen and the PC is not booting. Mainboard manufacturers were of course also happy to use that modules, because now they could use even less parts, and some even didn't bother to place a socket, so once the battery was low, the user was forced to replace the whole mainboard. Well, officially this has been made to prevent the battery from leaking, but we all know the real reasons. Anyway, the point is that such modules were designed to serve around 10 years, after which the battery should drain eventually, and with empty battery, neither time and calendar nor any other BIOS settings could be saved, so you'd have to go and buy a new module. Obviously, after 25 to 30 years, most of those RTC modules have already empty batteries inside, and today we have a lot of nice retro mainboards with a handicap. We needed an open source replacement, and so I introduced this solution, which was welcomed by the community very well. Essentially, this is the same module as the Benchmarq BQ3287 with a BQ3285 RTC chip, a crystal oscillator and a battery holder. As I open sourced this project, BQ3285 and compatible chips were not produced anymore, but there were plenty available as new old stock on known selling platforms. However, since I open sourced it, these modules faced a huge demand and thousands of those have been sold by various sellers. Not only because the modules were used in mainboards, but also in synthesizers, various tools, etc. Funny side note, I even got some angry mails because some modules were not working. People complained and asked for refund, despite that I never sold those modules, except of a handful to some community members which I know. This is a negative side effect when you open source something, I guess. Anyway, now we are facing the next problem. Meanwhile, the required BQ3285 ICs are mostly sold out everywhere. I have some in my personal stock, but not many, and so on some boards I started to come back to the old solution, which I presented before I made an own module. The solution is quite simple. Drill a hole in the housing of the module at a right spot to reach the pad of internal battery. Solder a wire and a battery holder for an external battery and you are done. I already showed it in some of my videos a long time ago, but if you are interested, follow the links in the description. So, as I said, the BQ3285 ICs are becoming rare recently, and meanwhile I try not to use my replacement module everywhere. And here is why this board, which I repaired in the last video, is so interesting for today's topic. As you see, there is a placeholder for a CR2032 cell battery near the RTC module socket. When we use such a module, doesn't matter if this one or the original Dallas, the battery is included, and there is no need for a battery on the mainboard itself. As I mentioned before, in such a module not only a battery is included, but also the RTC chip as well as the 32 kHz crystal oscillator. Now, if we look at this board, we will not only find the placeholder for the battery, but nearby also some unpopulated components, one of which is a solder pad for a crystal oscillator. And if we follow the traces from those pads, we will see that they, as well as the battery poles, are all connected to the socket for the RTC module. So on this board there is no need to use a complete RTC module, but we could solder the battery and the crystal oscillator into the mainboard and insert the right RTC chip into that socket. And so we come to the actual point of this video, the question, which chip is the right one and where to get it from? For obvious reasons, those chips are not produced anymore since many years. It is not too hard today to find a Motorola MC146818 or compatible Hitachi chip on some damaged 286 or 386 mainboard. However, they will not work in Pentium mainboards, since they are designed for integrated solutions, as I explained before, and an old Motorola chip is a slightly different pinout and needs additional circuits. Over the time, I collected many of such Dallas modules, and if you turn around one, you will clearly see the belly of the chip we need. Unfortunately, the modules are completely filled with resin, as I said, and getting the chips out was quite a journey, but it turned out to be easier than I thought. My first try was an absolute mess. Don't ever do this at home. You will not only ruin the chip, which you need, but also clean your workshop for the next 3 weeks. I used a Dremel tool to cut and sand down the plastic and the resin around the chip. The resin inside is extremely hard. It is even somewhat scratch resistant. Sanding it evenly is very hard, and it is not clear where the resin ends and other parts start. Long story short, that was a very bad idea, and if you ever thought about doing it that way, please don't. So my second try started with reading about resin a little bit. Don't ask why I didn't start with that step in the first place, but it turned out that with raising temperature, resin doesn't melt as I thought before. It actually gets brittle due to a chemical reaction inside. When it cools down, it gets extremely hard again. So armed with a hot air gun, a screwdriver and pliers, I practiced with some of modules, and after a little bit of practice, it turned out to be a child's play. First, you have to heat up the plastic cover round until you can squeeze a flat screwdriver along the edge. Then you just have to push the plastic to the side along the whole perimeter until the plastic cover falls off. After that, you just have to continue to heat up the resin, and as long as it's hot, press the screwdriver into it. It is so brittle that it just falls apart, leaving all the internals absolutely clean. The only places where I needed a couple of rounds heating it up and scratching with a screwdriver is between the pins of the IC. But even there, it wasn't a big deal to clean everything up in a couple of minutes. This whole procedure was even somewhat satisfying, to be honest. So I disassembled a couple of modules to find out what is the best temperature. You don't want to heat it up too much to avoid any damage on the parts. Luckily, you don't need to. As you see, this was my first try. The second, third, no, this was the third and this one was the last. As you see, the first part got the most heat. The plastic melted and it was too much. The second one I already didn't heat up as much, and the third and fourth it was less and less heat. I found that the best temperature is maybe around 70 to 80 degrees Celsius. The most heat you would need to remove the plastic cover, but as soon as it's down, the resin falls apart quite easily. As you see, the leftovers from the first try still have some resin inside. And it is again extremely hard. If I would want to get it out there, I'd need to heat it up once again. Otherwise, it would be even hard to scratch it. By the way, as I did this and realized how easy it was, I instantly thought about the Commodore C64 power supply, which is notorious for failing 5-volt rail. That power supply is usually filled with resin as well, and people don't even think to extract the internals, despite that the transformer is usually still alright and only the low voltage part has to be fixed. Taking into account how hard that resin is, that is fully understandable, but now, knowing how it reacts to heat, that could make it something easily doable. Probably for many of you this is nothing new, but for me it was quite a discovery. So my first try was a Dallas DS1287. Some of the pins on the IC are flipped up, and if you try to bend them down, they break very easily, so you might need to resolder the pins. However, I tried to run the IC as is, without the crystal oscillator or a battery connected, and the board was dead. That was kind of surprising to me, because it should run also without the crystal and the battery. I still can't explain the behavior, but as I soldered the crystal, which I got out from the same module, back to the broken off pins 2 and 3, the system suddenly woke up. Maybe this was some kind of coincidence, maybe a bad contact in the socket or something else, I'm not sure. In the next step, I removed the crystal oscillator again from the IC and soldered 2 new pins instead, which I made out of a copper wire. Then the crystal oscillator was soldered together with a battery holder for the CR2032 coin cell battery to the predefined places on the mainboard. I double-checked the continuity to the battery holder and the crystal, inserted the battery, the DS1285 IC, and started the system. It did post and reported back checksum, which of course was expected since no BIOS settings have been set so far. So I entered the BIOS, made some changes, saved, and got back checksum error message again. I repeated it a couple of times and it didn't want to work. Well, the mainboard did work before with my custom module, which is based on the BQ3287 chip. So I compared the data sheets of Dallas DS1285 with the Benchmarq BQ3287, and my mistake was obvious. Dallas DS1285 has only 50 bytes of general purpose memory, where BQ3287 has 114 bytes. Most probably this board needs that bytes to save the BIOS settings completely. So I disassembled a Dallas DS12887 RTC module, which has a DS12885 chip inside. That one is identical with the Benchmarq BQ3287. I'm still baffled how easy and clean it was. Here you can see that the chip has been made 1995 in the 48th week. The inscription on the plastic of the module is only 1 week younger, so the IC didn't have to wait long before it was set into resin. I could bend most of the pins back, however one pin for the oscillator broke off, so I had to solder it back. Some other pins didn't look very strong anymore, and I added some solder here and there as well to give the weakened pins some additional support. And as soon as the chip was inserted, the system posted. However, this time, as I saved the settings, the error message disappeared, the compact flash card was detected and the system started to boot into DOS. I removed the battery to see if the settings get lost, and they did, of course. And I also left the settings over a couple of days, and that worked either. First, I didn't populate the extra parts around the crystal. The system worked fine without those as well, but just in case, later I added a resistor with a value in mega ohms between the pins of the crystal oscillator and a decoupling capacitor to the battery for better stability. So, what is the takeaway from this experiment? Of course, that we can add a battery on the mainboard if there is a place for it and use an RTC chip, that was quite obvious. The question was where to get those chips from. I was quite worried about the growing RTC chip shortage, which are not produced anymore. The module, which I open source, is a good solution, but it is useful as long as we can buy the required ICs. Luckily, there is an easy way to extract everything what is needed from that old black box RTC modules, which are still there anyway. If you have a mainboard like this one, where a place for a battery and a crystal was provided by design, then you can do what I did on this board. Of course, you can also just drill a hole on the side and add a pin for the battery to the module. It will then be a similar solution as with an external battery. On mainboards which don't have a dedicated place for the battery, you can still use the solution with the external battery, or you can remove the case and the resin, solder a battery holder directly onto the pins instead of the old one, fix everything with a bit of hot glue and cover it with a 3D printed case if you like the original look. Just don't glue it again to be able to easily replace the battery later. Lots of new options, and I'm glad that I finally found the time to experiment with it. On more modern mainboards starting around Pentium times, even some later 486 mainboards, from there on until today the RTC circuit is integrated into the chipset. There are no dedicated components for that anymore, except crystal oscillator. That 32 kHz guy can still be found on most, if not every mainboard today. But on this channel we are mostly interested in the older stuff. That's why I'm happy to have more options for the repairs. And I hope you found it useful as well, or at least enjoyed this small journey. Please write what you think about it. I'd be also glad to know if someone already used the same heat trick to remove the resin from C64 power supply unit. That one is a beast. And this is it for today. Thank you for watching and goodbye.